Welcome to the next aspect of pressure level and terminology, and that is the part 2 of the previously discussed pressure level and terminology under the heads of chemical process utilities. Now, in the previous lecture we discussed about the different aspect of pressures, different type of terminology which are being used in this particular chemical process utility aspect. Then we discussed about the behavioral aspect of gas. We discussed about the different laws associated with the prediction of the gaseous behavior, Charles law, Boyle's law, then combined law, Gay-Lussac's law, etc. Then we had discussed about two numerical problems which are directly associated with this particular chapter. Now, in this particular chapter, we are going to discuss a couple of more numerical problems which are directly attributed to this particular theme. So, let us start with the numerical problem number 3, because two problems we have already discussed in the previous chapter. Now, here the two containers, they are having the volume of 2 liters and 3 liters, and they are separated by a valve as depicted in this particular figure, and you see that we have the valve. Now, that 2-liter container was initially at a pressure of 1.5 atmosphere, while the second container is having the pressure of say 2 atmosphere, and the valve suddenly opens and the gases they start mixing to each other. Now, you need to find the final pressure in two containers, assuming that there is no heat loss during the process. So, let us solve this particular problem. Now, this particular problem can be solved using both either Boyle's law or ideal gas law. So, let us talk about the first method using Boyle's law. So, it is P1 V1 is equal to P2 V2. So, the first container (1.5) into 2.0 liter equal to X pressure into 5 liter. So, X comes out to be 0.6. Now, second container (2 atmosphere) into 3.0 liter, this is equal to Y, that is the pressure 2 for the second container, into 5.0 liter. Then Y is equal to 1.2 atom. If we sum up both the containers, then both the pressures, that is P1 and P2, the 0.06 atmosphere plus 1.2 atmosphere, and that is 1.8 atmosphere. Now, if we take the ideal gas law into consideration, one, that is PV is equal to nRT. So, we need to use this particular formula twice. So, 1.5 into 2 liter is equal to N1 RT. So, in the first container, the gas moles is equal to N1 3.0 upon RT, or 2.00 into 3.00 is equal to N2 RT. Now, in the second container, moles of gas is equal to N2 is equal to 6.00 RT. Now, second aspect, that is PV is equal to nRT. So, the total volume 2.00 plus 3.00 is equal to 5.0, and the P3 5.00 is equal to N1 plus N2 RT, and P3 is equal to 5.0 is into 3.00 upon RT plus 6.00 over RT to RT, and P3 is 5.0 into 9.00, and P3 is comes out to be 9.00 upon 5.00, and that is 1.80 atmosphere. Now this is again, if you see that we have got the 1.8 atmosphere both from ideal gas law as well as Boyle's law. Now let us take up another problem, that is you need to calculate the change in the temperature when 2 liter gas at 30 degrees Celsius is compressed to 1 liter. Now here you see that we will utilize V1 over T1 is equal to V2 over T2, and 2.0 liter over 303.15 Kelvin, and is equal to 1.0 over x. Now if we cross multiply, then we get 2x is equal to 303.15, or x is equal to 151.58 Kelvin. Now change in temperature is equal to final temperature minus initial temperature. So this is 151.58 minus 303.15, and that comes out to be 151.57 degree Celsius, and that is my answer. Now let us take up another problem, that is the problem number 5. Here you need to find out that what change in the volume results if 60 ml of air is cooled from 37 degrees Celsius to 100 degrees Celsius. Now let us discuss the solution. Now here T1 is equal to 37 plus 273.15 is equal to 310.15 Kelvin, and T2 is equal to 10 plus 273.15, this is equal to 283.15 Kelvin. 60 ml over 310.15 Kelvin, this is x over 283.15 Kelvin. Now if we cross multiply, then we will get 310.15 into x is equal to 16989, or x is equal to 54.78 ml, and this is the final volume. So the volume decreases by 60 minus 54.78, and that comes out to be 5.22 ml. So in the another problem, you consider an ideal gas with an absolute temperature of say T1. Now to what absolute temperature would the gas need to be heated to double its pressure? You need to express the answer in terms of T1. Now here the P1 over T1 is equal to P2 over T2. Now we want the pressure to double, so set P1 is equal to 1 and P2 is equal to 2. the units don't matter because they are the same, that is atmosphere, kilopascal, whatever, mm, hg, torr. It does not matter which one you use. Now, we want to see what the temperature does. So, set T1 to 1 Kelvin and T2 to, let us say, X. The temperature does matter. It must be in Kelvin. So, therefore, 1 over 1 is equal to 2 over x, or x is equal to 2k. So, the answer is that T2 would have to be double the value of T1. Now, in another problem, a gas has a pressure of 699 millimeter of mercury at 40 degrees Celsius. Then you need to find out that what is the temperature at standard pressure. Now, here the temperature, the pressure is given as 699 millimeter of Hg, and the temperature is 40 degrees Celsius, and that is 273 plus 40, it comes out to be 313 Kelvin, and you need to have the standard pressure. What is the temperature? So, standard pressure is 760 mm of Hg. So, let us solve this small problem, and that is, so we can write that 699.0 mm Hg over 313 Kelvin, this is 760.0 mm Hg, that is standard pressure, over, let us say that X is the desired temperature. So, upon solving, we get this is 340 Kelvin, or 340 minus 273, this comes out to be 67.0 degree Celsius, and that is our desired answer. Now, in another problem, a gas has a volume of 400 milliliter at minus 18 degrees Celsius and 280 torr. Then what would be the volume of the gas, or to be at 360 degrees Celsius and 840 torr of the pressure? So, let us discuss the solution. Now, there are various steps in this particular solution. One is that set up all the problem values in solution matrix. So, let us form a small table for this one. Here P1 is equal to 280 torr, P2 is equal to 840 torr, that is given in the problem. Then V1 is equal to 400 ml, and V2 you need to calculate. So, if you see that we are having 400 ml, and T1 is equal to 255 Kelvin and T2 is equal to 633 Kelvin. You see this and this. So, the second step is the combined gas law is rearranged to isolate V2. So, V2 is equal to P1 V1 over T2 upon P2 T1, and that is 280 into 400 into 633 upon 840 into 255. The third stage values are inserted into it, and V2, which is desired one, V2 comes out to be 330.9 ml, and that is the answer. Now, another problem. Suppose the pressure on a 10.0 meter cube sample gas at 12 degrees Celsius is cut in half. Now, there are two parts. One is that is it possible to change the temperature of the gas at the same time such that the volume of the gas does not change? Now, second part is that if yes, then calculate the new temperature of the gas. So, let us solve this particular problem. The solution to the problem statement number 1. Now, we can't answer this without doing the calculation for part B. Now, this is because the temperature must go down to keep the volume at 10 meter cube. Now, if the temperature must go down to absolute 0 or below, then the answer would be no. Otherwise, we would answer yes. Temperature must go down because of this. The pressure went down. Therefore, the volume went up, assuming constant temperature. Now, in order to get volume back to 10, we must cool the gas down. Let us again taking one assumption, constant pressure. Now, we can discuss the solution to part B. Now, use the combined gas law. Now, the combined gas law is rearranged to isolate T2. Now T2 is equal to P2 V2 T1 over P1 V1. Now we can take any value of initial pressure while considering the final pressure to be doubled. Now take it 1 atmosphere. So final pressure will be 2 atmosphere. So T2 is equal to 1 into 10 into 285 upon 2 into 10, and that is 142.5 Kelvin, and this is 142.5 minus 273, and that is minus 130.5 degrees Celsius. Now changes to Celsius to get minus 130.5 degrees Celsius. So the answer to part A is yes. Now let us talk about the next problem. Now here a cylinder with a movable piston contains 2 gram of helium at room temperature. More helium was added to the cylinder, and the volume was adjusted so that the gas pressure remained the same. Then how many grams of helium were added to the cylinder if the volume was changed to from 2 liter to 2.7 liter, and temperature, you may assume that the temperature was held constant throughout the process. Now let us talk about this one. Now first thing, convert grams of helium to moles. So first thing we need that the molecular mass of helium is 4.00 gram per mole. So 2 gram upon 4 mole, that is comes out to be 0.500 mole. Then second thing is that you can use the Avogadro's law. So V1 over N1 is equal to V2 over N2, and that is 2 upon 0.0 upon 0.5 mole equal to 2.70 liter upon X. So X is equal to 0.675 mole. Then compute grams of helium added, and that is 0.675 mole minus 0.500 mole, and that is 0.175 mole. So 0.175 mole into 4.00 gram per mole, which is equal to 0.7 grams of helium added, and that is my answer. Now the last problem for this particular chapter is that 2 piston of hydraulic lift, they have the dimension of 50 centimeters and 5 centimeters. What is the force exerted by the larger piston when 80 Newton is placed on the smaller piston? Now solution of this particular problem, that since the diameter of the pistons are given, so we can calculate the radius of the piston, and that is r over d by 2. So, the area of smaller piston, that is 3.14 into 5 by 2 whole square, that is 3.14 into 2.5 square. Then 3.14 for the second aspect, 50 by 2 square, and that is 3.14 into 25 square. So, F2 is equal to, that is force in the second aspect, A2 upon A1 into F1, and that is 25 square upon 2.5 square into 80, and that comes out to be 8000 watt. Now, this means with force of 80 Newton, the weight of 8000 Newton can be lifted. So, that is the answer. So, in this particular chapter, we discussed the different type of numerical problems which were related to the pressure and the gas law. Now, if you wish to have a further study, then we have enlisted different references. You can utilize the things given in these references for your need. Thank you very much.